If you have not yet downloaded and printed the example KP 7.1 associated with instrument accuracy, then please do so. Print it out. If you don't have access to that for some reason, then all is not lost. Simply stop the video and write down what you see here, and then we'll charge along. In example 7.1, we're going to look at a specific example of how to deal with instrument accuracy in the context of joint distributions. And ultimately where we're headed here is to let this example of discrete data draw out a variety of different things, such as the joint probability mass function, the marginal functions, the conditional functions, and even get into a little bit of error analysis, as well as get into dependent, or set the context for dependence and independence that we'll be getting into in the next lesson. Note that what we're doing here in this specific example is we're taking a look at an observation point on a highway and the number of vehicles that are passing in a 30-second interval. The actual number here is a random variable x. Right, the instrument data is y, recorded during the exact same 30-second interval. So someone has gone out and done the calibration exercise to record the actual and compare it to what the instrument was doing. Right, so you have a data table down here that's blank at the moment, and for whatever reason at this point in the highway, there was never more than a total of 4 vehicles that arrived in this 30-second interval. And note that we've ultimately recorded 400 total intervals. And so we've got this 0, 1 through 4 on both axes. Y is the vertical axis, is the what was recorded. And there's a lot of reasons why you might have some imperfections in the instrument. This particular kind of instrument is the pneumatic tube that gets stretched across the highway, and some of these imperfections are related to dynamics, vehicle dynamics, that they may have been hit some sort of bump, and so when the wheels bounce across, they might actually not be quite solidly on the road, and therefore that they don't trigger the mechanism. You also end up having mechanical limits of the device that sometimes then make an imperfect recording. And the data that we have in this specific example is that in 100 of these 30-second intervals, we've had no traffic actually happening, and we've had no traffic recorded. In 16 of these, we had an actual single vehicle but no recorded, and in 4 of those we had 2 vehicles that arrived and yet nothing was recorded, and then on out we had 0 for the real high range. Okay? As we go to the next one, where we have recorded 1 on the data recorder, in this particular instance, we're never going to show that we have more recorded than what was actually happening. So this lower triangle of this table and really lower triangle of the matrix is all going to be zeros. And so we get 1 occurring, 1 recorded, happens 144 times, and then on horizontally, then 12, 4, and 0. Next one, where we have 2 vehicles and 2 recorded, happened 64 times. and then an error of 1 here 8 times, so actual 3 but recorded 2, and we had once again an instance where we had 2 errors associated, so 4 actual, 2 recorded. Then 3 and 3 is 28 times, 6 times we had an error of 1, and then finally we had 13 times that we had 4 recorded, and 4 actually did happen. Okay. So that gives us a total of 400 30-second intervals. Right, I'm going to slide this on up. So we're going to be doing a number of calculations, and so one of the questions that we were interested in is, well, what's the probability that the recorder is correct? Right, and what we're saying in that instance is that our x was equal to a specific value and our y was equal to that same exact value. And we're asking, well, what's the likelihood that that happened? We're going to sum that over all of the xi. And note that that really is just the diagonal. Right? So in that calculation then, we had 100 out of the 400 were 0 and 0. We had 144 out of the 400 that were 1 and 1. We had 64 that were 2 and 2. We had 28 that were 3 and 3, and we had 13 that were 4 and 4. Add that all up, we get 349 over 400, and that is equal to 0.8725. There was our probability of being correct. Right? You could also, of course, ask the follow-on question that, well, what was the probability of error? And the simplest way to do that is, well, that's just 1 minus the probability of correct. So that would be 0.1275, so almost 13%. From a standpoint of how you might write this out in math, shorthand notation that is, one way we could look at this is what we call the joint probability mass function. Right? That's really what we had up here before, that this guy was our joint probability mass function. In general, that would be xi and yi. For this very specific case that I have up here, well, the y was equal to xi, so you would substitute in the xi right in that particular spot. Right? And down here, then, we're going to actually do a double sum of these probability masses. Right? We're going to do all of the xi values, and then we're going to sum over all the yi values that don't equal the xi. So we could be summing up all of these relative frequencies that are off of the diagonal. Be another way to go about this. And so we go back in this very specific case that the joint probability mass function can be found as the table above in the form of relative frequencies. Right, we've written it at the moment in terms of total frequencies observed, but all we have to do is divide each and every one of those by 400. Likewise, there's a lot of really important, valuable information that we can also get out of the table just beyond the joint information. For instance, if we were to ask the question, well, how often was it that the instrument recorded 0? Right, well, that would just be from the sum all the way across this table. And so that would be 100 plus 16 plus 4, or 120. And then, likewise, how many times did we have the record of just one, sum across horizontally? That comes out to be 160, and those sums continue on, 73, 34, and then 13. And as relative frequencies, so that would be out of 400 in each case. And what we've just done there is that we've come up with the marginal distribution for y. Py, probability that y is equal to y sub I. Right? And so what we did mathematically was we summed over all of the xi the joint values xi and yi. Likewise, we could do the same thing to get the marginal for x. We have 100 here. We'd have 16 plus 140. There's 160. We get 4 plus 12 plus 64 is 80. And then we get 4, 8, 28. They give us 40. And 0, 0, 1, 6, 13. We get 20. And that's your probability mass function for xi. Of course, divide that by 400. In each case. And there again, that's a marginal distribution. So you can see there's an interesting relationship here between the joint and then the individual ones. Oftentimes what's going to happen is that we're only going to have data associated with what's recorded. What we want for design purposes, well, what actually happened out there. And you see in this particular instance for this recorder that it's only about 87% accurate. And that's something that they'll add some fuzz to our design that we'll have to deal with at some point. And that's true not just of collecting information related to traffic, but also, of course, related to any instrument that you might be looking at. Before we go on to talk about another small topic here, I want to first talk about the conditional distribution. If, for instance, we were curious about, well, what's the probability that x was equal to 2, yet our instrument recorded only 1, and so that's a very specific instance of an error. We could look at the probability that x is equal to 2 and y is equal to 1, and then normalize that by the probability that y was equal to 1. Right? That's just the definition of the conditional distribution. All right. And so if we take a look at how often was it that x equaled 2 and y equaled 1, right, well, we come back up to our table. X equals 2 is right here. And y equal 1 right there. So that's 12 out of 400. And then probability that y was equal to 1 was 160 over 400. And so we get 12 over 160, and 12 divided by 160 is 0.075. So only about 8% of the time did that particular situation happen.